Okay, I think we've accreted about as many people as we're going to accrete. I wanted to remind everybody of a pop song from last year. It goes, hey, I just met you. Our network's flaky, but here's my packet, so call me maybe. My name is Kyle Kingsbury. You might know me as Afer online. Some people think that I'm a company called Jepsen Networks. Yeah, like, I don't know. I just it's this personal blog, but they think it's a company. And I'm not a company. I'm a person. I work at a company called Factual, and my job there is to keep databases happy. I try and make our React cluster, our Elasticsearch cluster, our React or our Zookeeper cluster. All these things need to run smoothly and happily, and there's care and feeding of HBase involved. But when I'm not making distributed systems happy, I'm torturing them relentlessly. The title of this talk is called Jepsen 2, Linearizable Boogaloo. The fact that this is in fact the third Jepsen talk should suggest something about how important linearizability is. Jepsen is a project where I subject a distributed system to certain operations like reads and writes, things that you don't expect databases to do. And then during these operations, I cause network partitions, I cause disk slowness, I screw with clocks, the things that can happen in a real production environment. And then I measure what happens. You write down every operation, and you look at the history and try to reconstruct like a air traffic investigator right after a crash. You're like, what? You find this mile-long streak of plane parts, and you're trying to figure out, oh, there was operator error at 200 feet. You're probably wondering, like, why do we care? You all showed up to a talk which had linearizability in the title, which suggests that you're either crazy or don't know. The real reason, my lord, is that the night is dark and full of terrors. Really, though, asynchronous networks, the sort of networks that you and I work on every day, are allowed to drop, to delay, to duplicate, and to reorder packets. This should terrify you. I mean, this is awful, right? Like, you send a message and it just doesn't go anywhere, or you send one message and you get 5 copies. You get a copy in a year. Is that okay? How do you build a system that actually does what it's supposed to? And real networks, IP networks, do all of these things, and they do them especially in the cases of network partitions, right, which are just really long delays, really long drops. Network partitions don't have to happen in the network, right? People think the network's reliable, but it's not. And even when it is, garbage collection can look just like a partition, right? It's a pause in the runtime, so no messages get through. Network maintenance, right? Human error, which is really system error coupled with the human. Seg faults, crashes, faulty network interface cards. Broadcom is famous for this. Broadcom NICs will take packets in but not out, or they'll drop packets once you get to a certain volume, or they'll use flow control packets in the DDoS the network. Bridge loops, spanning tree issues. If you host your network with somebody else, like AWS, you're subject to all of their network problems. You're subject to remote hands that think rewriting your etc interfaces file is a good idea because you asked them for a sudo access. You'll see all sorts of terrible things happen, right? These are real problems. And in the face of those problems, you want to maintain some sort of intuitive correctness. Do the right thing. Well, what's right? No, I don't know. You tell me. Here's right. This is the right that we learned when we started programming. I've got a variable. Let's say x equals a. And if I read x, I print x, I get a back. And I print x, and I get a. I'll write b, I'll read b, I write c, I write d, I read d. Things happen in nice single order, right? In program order. Most languages work this way. This is a concurrent program. If you think about Node.js, right? This is Node.js's model of concurrency. Everything happens in one order. There's only one thread, right? Things are just linearly going through the system, but sometimes you switch contexts. You switch to a different sort of process. So maybe you go from writing A, and then somebody else reads A. You go to a different callback, right? And that thing sees it. And then that callback does something. Maybe the callback writes B, and then you come back to the original thread of control, and you read that B value. So I didn't write B, but I still got to read it. This is somewhat less simple, but it's still understandable, right? This is a very simple, controlled, sort of atomic model of concurrency. But this is what's actually happening. You are not at the source of truth. If I want to go write a variable over here on the screen, I have to walk to it, I have to write it down, and I have to come back. And if I'm talking to RAM, that's what, 11 nanos? It's terrifying, right? You have to spend all this time going to memory. And that means that in the time that I go to memory, somebody else could also be going to memory. So maybe I'm writing something at the same time as somebody else is reading something. I send a message, it takes time to come back. There's a difference between the invocation and the completion of the operation. And that means weird things can happen, right? That delay in messaging means that the order of events in your system is less well constrained. But it's still somewhat linear. Operations are still happening in a single order, right? This is called linearizability. There's atomic transitions from point A to point B. And even though we can get weird consequences, there's still that nice underlying source of truth. I can initiate a read at this bottom process, and I'll start reading and I'll see A, right? A is the value currently. But by the time my message gets to the source of truth, gets to the actual register in RAM, or gets to some other system on a different continent, somebody else might have snuck in and written B, so I'll see B. Or I could see A. It depends on the order in which the message has arrived, right? It depends on queues and networks and physical delays. But there are finite bounds. Messages can't go backwards in time, right? We don't have tachyon networks. So the fastest I could possibly read something is right now. And the latest I could possibly read it is the moment before it comes back to me. So there's a window of time from invocation to completion, and those are the states that are going to possibly play into my final value. And that gives us invariance, right? A linearizable system, a system that works like this, has the invariant that once I complete an operation, its consequences will be visible to everybody afterwards. So if I do a write of B, some concurrent read could see A, but a non-concurrent read, a read which happens after I complete the operation, is guaranteed to see B always. This is a really good constraint, right? We get no stale reads. We can do safe mutation. You can do compare and set. You can do transactions, right? This is the linearizable basis for a strongly consistent system like Postgres, right? Strong serializable systems. Come back to that one. Everybody sees the same order of states, and they agree on the times. Right? You might not agree precisely, but you have a bounded window during which you're allowed to see a state. This is the same sort of property you use to programming with. If you work in a language like Java, right, which has a volatile type, volatile memory reads are guaranteed to be visible once written. So you do a write in a volatile memory, right? It's visible to all threads subsequently. If you do a write to a regular variable, it's not, right? There's this thing called sequential consistency, and this is where all operations happen in the same order, but they might be skewed in time. So if you just write to a non-volatile field in Java, right, and you do a read from some other thread, you might get an old value. But there's still a constraint that everything happens in the same order. Your lines can't cross. I can't read B then A. I can only read A then B. This is good constraint. It's still weaker than linearizability, right? We can still read things from the past. This is the same consequence you get with queues, right? You get a web request, and I'm gonna process an image maybe. So I throw it on a queue, and I return, OK, I've accepted your request. If they do a read, they won't see it done, right? Because it's in a queue. It's not ready yet. But if the queue completes later on, then it'll be visible. So this is a sequentially consistent system. You do this all the time in your production systems. Serializability. We can relax the constraint even further. There is an order, but fuck if we know what it is. Like, a serializable system can literally compute any order it likes of transactions, so long as every transaction holds consistently. So like, if it's valid to do a read at any time in the universe, you could do that read. So a serializable system, a trivially serializable system, could be like dev null. If you just do a register and all you have is reads and writes, all of your writes you can throw away, and all of your reads happen at time 0. Problem solved. I built a database. But really, what makes serializability a strong constraint, it's still relatively strong, is that when you're doing multi-object transactions, the number of possible orders is constrained strongly. So a business-consistent system where all state transitions happen in the right order, that can be serializable. And that's actually somewhat difficult to obtain. But trivial things like reads and writes of registers, those you can blindly reorder. You're thinking, hey, like, isn't that ACID consistency, like serializability? It's actually not. Serializability in ACID, serializability in the database literature, this is all very confusing. That's actually referring to linearizability. It's like a strong serializable. It has to happen, and it has to happen on time. So we all have acronyms we like. My favorite acronym, MRB, a gentleman in New York, has told me that acronyms are easy to make shit up about, so I'm going to proceed to do that now. My favorite theorem, among many, is the CAP theorem. You might have heard consistency, availability, partition tolerance. Pick 2 out of 3. That's nice and simple, right? Memorable, catchy. You probably sing it to your children at night. CAP consistency means exactly one thing. It means linearizability. If you use CAP to talk about any system other than a linearizable system, it is wrong. It's a theorem, right? It has precise definitions, precise proof. It can't be wrong because it's a theorem. It's proved. If you disprove CAP, you've disproved lots of mathematics. Availability in CAP means that every request to a non-failing node must succeed. That's a really strong constraint, right? Every single node has to respond. If you have a network partition and every single node is isolated from every other node, they all have to be able to service requests. That puts some pretty strong bounds on what we can do, right? And P, partition tolerance, is mandatory. You can't not choose it, right? Real systems can and do partition. I've written a lot about this. I don't have time to dig into it, but rest assured, these will happen to you. They're rare, right? But when they happen, they're catastrophic, so you really need to worry about it. So you can pick AP systems or CP systems at maximum. You can have that total availability, you can have that linearizability, but you can't have both at the same time. Some people say they do both or that they work around it, but they really don't, right? It's a theorem. You can't not do it. Typically, when somebody says they've beat CAP, either what they have is like a system which is C and A, it's consistent and available, linearizable and available during a healthy network, and then when the network is broken, it explodes and loses data. You're saying, hey, it's more complicated than that, right? There's more models. You could have weaker types of consistency, right? There's actually infinitely many models. So I've talked about linearizability. There's also the consistency model of linearizability plus histories in which on Thursday John reads yellow. That's a valid consistency class. So you could define as many of them as you want, but there's some big families. And what's interesting is that we have proofs about a lot of them. Stuff in red up at the top, that's the stuff that you can't have fully available. You can't have linearizability. You can't have like ACID linearizability, which is that strong serializability at the top. You can't have sequential consistency, repeatable read, snapshot isolation, or cursor stability. All those things are ruled out by different theorems. But if you relax the constraint about availability, if you say that a node has to talk to a particular server and it's stuck to that server, then you can recover a little bit more, right? You can have a fully available system with that sort of sticky availability and still preserve causal consistency, where only explicitly causally related writes are held together in sort of correct order. You can have PRAM, which is a sort of memory consistency model that most processors use. You can have read your writes. And then if you go weaker still, if you have monotonic reads, all reads happen in ascending order. Monotonic writes, all writes happen in ascending order. Read committed, monatomic atomic view. Lots of other consistency systems. These are the ones that like Riak and Cassandra give you, right? Or even weaker, like they make no guarantees. You can have these highly available systems for your sort of weak consistency where lots of histories, lots of interleavings are okay. And then for the stuff where only one interleaving is okay and you really want that strict guarantee of transitions, you use the strong stuff up top. When I say weaker, I mean that there are more allowable histories, that the class of operations you're allowed to see, the class of weirdness, is smaller. And those models are more available under failure modes. They're also weirder, right? Because more stuff can happen. You can read values from the past, you can write to the future. But they're also faster. If you look at a modern CPU, they're not linearizable, right? They will reorder your operations, they'll reorder your reads way to the future, way to the past, and you have to ask for strong serializability. So there's a performance trade-off to be made as well. Finally, I want to note that safe and weak are different things, right? Strong linearizable systems can express a broader class of problems safely. You're not going to lose operations. But some nonlinear histories can be expressed with CRDTs. So you can have a system where like your history is nonlinear, and there's multiple points of truth at any given time. Nobody really knows what's going on, but every operation eventually adds up to something stable. That could be an okay, safe model for your actual business logic. So I'm testing databases, right? Theory's done, you can relax. I wanted to get this out there because there's really no good resource for it. And I'm probably getting some of these things wrong. I've been reading the literature, it's very confusing. People reuse the same names for different things. I don't advise it. So I've been testing a lot of databases, Zookeeper, NuaDB, Kafka, Cassandra, Redis, Riak, Mongo, and I found a bunch of bugs in these systems, but most of them weren't strongly consistent to begin with. When people asked me, hey, can you test etcd, I couldn't find problems. And the reason I couldn't find problems is because the way I test these systems isn't really fully testing linearizability. I do a bunch of compare and set operations. Add 0 to the empty set, add 1 to the set of 0, add 2 to the set of 1 and 2, and you do that concurrently, right? Some of them fail, some of them succeed. You look at all the ones that succeeded, and those are supposed to be present in the final set. So you do one read at the very end of all these operations. But the system could lie, it could cheat, it could slide those operations around in time and not make them visible until the very end. We've got these sort of big truck-sized gaps in the consistency checker that you could drive your database through. So I got to thinking, how am I going to test those sort of in-between times? I did a bunch of stuff blindly, I'm funneling around in the dark, and then I finally open up the box and look, and at the end it seems like everything worked okay, but what actually happened in the box? Can I tell by touch alone? So I built this thing called Nasos, which verifies this linearizable property. So Jepsen now does the installation of databases, and it sets things up, and it creates failures, it schedules operations, writes down a history, and then it passes it to a checker. And the checker, Nasos, says, hey, let's find out if this thing looks like a linearizable system or not. So you need a way to verify, is the transition okay? Everything happens in some order, so how do we verify the order itself is all right? You need a model, right? Like a function that takes a state and an operation, like read the number 1, and then it's going to return a new state. If you do a read, it'll be the same state, right? Unless you tried to read, say, 2 from the number 1, and that's not going to work, right? You don't want to see that, so that returns inconsistent. So you could say, all right, let's define a data type called mutex. Maybe we're going to model a lock, right? It's going to have a state. It's going to contain a little locked Boolean, and it's going to implement this model interface. Every time you step this model forward with a new operation, we take a look at the function f of the operation. If that function is equal to acquire, take a look at the locked state. If it's currently locked, you can't acquire an already locked mutex, right? So that's inconsistent. And if it's unlocked, we can just return mutex true. If you want to release, it's just the opposite, right? So this really compact definition, right? We don't know a whole lot formally about this. We're not doing like a proof. This is an experimental method. But that method lets us verify that a given history is actually okay or not. Like I can write 1 and read 1, and that works out fine. I can write 2, and then if I read 1, oh, that's not going to work, because the read 1 is going to return inconsistent. It says, I can't read the value 1 from the register 2. That's not okay. So bingo, we solved the problem, right? We're done. Except that we don't actually know what happened inside the box. All we know is what happened outside the box. We've got our concurrent clients, right? They're all doing things at the same time. And they've got their own independent pictures of the history. And we have to figure out what the actual linearization was. So client 1 invokes, and then concurrently client 2 invokes, and concurrently client 3 invokes, and client 1 completes. So you've got some order, right? But it's overlapping. And then there's this nemesis process who's busy initiating failures and stuff. We don't care about that. If a process hangs, it's really bad. If you crash or if a database throws an exception, you don't know if that operation is going to happen. It might happen now. It might never happen. It could happen in 2 weeks. So you have to hold on to it. It's as though it was always concurrent with every other process until the end of time. And that actually turns out to be a real problem, right? Because think about how many linear histories there are. One's I could write 1, I could read 1, I could read 2 and write 2. That's an okay way to move through this path, right? I'm always going from left to right, forward in time, and just sort of jumping between these histories. But if I chose a different one, read 1, write 1, read 2, that's invalid. Anyone want to take a guess at the sort of computational complexity? How many possible interpretations are there of a history with n concurrent actors? Anyone? Well, any one of these could happen or not happen, right? So that's subset, no power set, yeah, okay, power set, and then you need to order those things. You get the permutations of every power set of the operations which are concurrent, and that's n factorial, which has a special kind of O notation for computer scientists. And you look at this and you just start pulling your hair out, and you beat your head against the problem for a while, and you start thinking, all right, maybe I can find some degenerate states and paralyze the system somehow, and that'll give me some speed up, and then let's try. I don't know, what's degeneracy anyway? What can we make the problem smaller? If you and I both write 1, it doesn't matter what order we did it in. The current value is going to be 1 either way. And if we're going to have the same history of operations after that point, if the state is 1, it doesn't matter which path we take. They're both going to linearize equivalently. So we can just throw away whatever history has come to the same state in the same future. That's degeneracy, right? If our system has a high degree of degeneracy, like a mutex, right? Only 2 states, on and off, locked and unlocked. Well, in that case, a whole bunch of stuff is going to collapse on that unlocked state, and you can then discard thousands or millions of possible worlds per iteration. And since every one of those things explodes into a million more worlds every step, that turns into a really big reduction. We can parallelize. If I get an invocation, I've got 2 branches to follow, one in which it happens and one in which it doesn't. So I could do both of them at the same time. And once I see an operation complete, I'll kill off the fork that didn't have it happen, because I know this event actually happened. If I get concurrent invocations, I get up to n factorial splits, and typically there's millions to tens of millions of outstanding sort of world lines being explored, and all of them can happen independently, so we just throw them on threads. And then we can do it lazily, right? You don't have to actually solve these things all at once. You could say, that path looks really expensive, I might take it later, but I'll hold off for now. And if you're exploring, think about this like a maze, right? You're trying to find your way through a maze with a whole bunch of friends. All of you take different routes, right? You're following different sort of world lines, different paths. And then if you hit a dead end, you color it in black on the way back. And that way, if you look at the floor, oh, that path is colored in, I can't take that. Somebody else has already gone there. So that means you can save work, right? We memoize the results of execution. So you're thinking, okay, it's parallel safe. We represent the whole state as this sort of data structure, so we can parallelize it and represent it as this first-class citizen, do backtracking. All this sounds an awful lot like this weird idea that Margot Seltzer was talking about last year at Recon. She said, hey, what if we took x86, like this big, complicated, stateful machine, right? Like, you can't automatically parallelize an x86 program. You need a compiler to do that. But if you think about it, like, what is a computer? It's a vector of bits, right? It's like a bunch of registers and then a bunch of memory, including the program state, right? And an x86 processor is just a function that takes a 32 gigabyte register or whatever and like moves it forward 1 step. And just keep going and going and going, and you get that's a computer, right? So if you've got space for like lots and lots of 32 gigabyte vectors, you could just write it down, right, in memory. Problem solved. And if you ever see a point where you could like speculate that maybe you're going to do that execution later, you could just write down that vector and have somebody else solve it. And if you ever hit that point, you could jump ahead to wherever it was going to be. So you can think about cases where you could automatically parallelize these sorts of unknown, opaque state machines, just like the state machine that we're trying to check for linearizability. And those of you in the audience who are Haskell fans are thinking, man, GHC is looking really attractive right now. You're shouting, Shrogdor! Well, I'm not quite as good a Haskeller as I should be, and although there's a lot of monads in this system, we just don't call them that. Shh. Over in Closure Land, where we're all Sith Lords, we like to call them state. So we exploit Closure. We use the shared structure data structures. If you have a map or a vector in Closure and you add something onto it, you get back a copy, but it's not a complete copy. It's just the difference plus a reference to the original data set. And that means that when we want to fork the world into like 13 million different paths, it's actually pretty cheap because they're all going to share structure with the original. So a lot of these problems become a little bit more tractable. You say, okay, well, I've got this list of world lines. I'll just throw parallel map on it and like problem solve. And that works surprisingly well. Except it starts to break down where you want to do like out of order execution. We want to memoize and defer things. So we can't quite map linearly anymore. So we need a little bit of JV immutability. So we take advantage of CliffClick's high scale lib, which actually turns out to have some contention points in it, but it parallelizes much better than the standard Java concurrent hash map. Striped wrapper for Java to a priority queue. Priority queue is incredibly slow because it does a whole lot of lock acquisition, but if you stripe it onto multiple threads, it can go really fast. You can take advantage of the atomics for unboxed state, and then closure atoms, closure futures, closure references, all those things work really well. Very good concurrency story. Immutable pure functions for these sort of internal hard bits, and then on top of that, this mutable scheme that gives you high performance. The Comcast shows up, and they say, we here at the Empire would like to give you a little research grant. Can you think of anything you'd like to build? And I'm like, fund my moon laser. So I build a moon laser. This is Nasos running on all 48 cores of my desktop. This is a Xeon 2697, 2 of those, 64 megabytes of L2 cache, or L3 cache. and a roughly 60 gig heap. So this is not a problem that's tractable unless you have hardware for certain types of histories. Some types of histories are easier, and you can trade off space for performance, but it's computationally hard. And having this money made it actually tractable for the first time, at least for me. So you look over and you say, oh, you have a different target, a military target, then name the system. etcd. They're on etcd. Well, first we'll deal with your friends on RabbitMQ, and we'll come to that. So let's blow up Rabbit. RabbitMQ is a message queue. It's built in Erlang. It's distributed from the ground up. It knows about worker state, worker tasks. Put things in, they come out somewhere else, and then you can reprocess them. It speaks AMQP, all very good, right? And you think, oh, let's make a lock out of it, because I like turning systems into other systems. And the Rabbit docs are actually pretty clear that partitions are going to ruin everything. One of the things that they're clear about is that if you have a network partition, you can actually lose data in your queues. I haven't managed to prove that yet, but I suspect it can happen. You'll see, in the event of a network partition, Rabbit say something like, amnesia, inconsistent database running partition network. This is an Erlang distributed database called Amnesia that sits inside of RabbitMQ. And when this happens, sort of all bets are off. And you're thinking, can you really make a lock service out of this? But the RabbitMQ team says you can, so let's try it out, right? Like distributed semaphores, RabbitMQ. What are we going to do? We're going to take a single element queue and one task in it. You get it. And as long as you've got that task, you hold the lock. And when you're done, you say, yep, cancel that, put it back in the queue, and then Rabbit hands it off to somebody else. Straightforward, right? And the limit, the fastest it could possibly be handed off to somebody else if Rabbit is linearizable is for me to hold the lock. I release it. It passes through Rabbit, pops out the other side. Somebody else holds the lock. Notice the black bars don't overlap, so our lock is safe. The mutex is safe. It's mutually excluding. Only Rabbit's not quite linearizable, is it? Because if I crash, Rabbit's going to recover, and it's going to hand off that record to somebody else. This is good, right? You don't want a deadlock. If I crash, you don't want to never hand off lock to anybody else. You should detect it. But there's no such thing as reliable failure detection in an actual network, right? So when you lose network connections within RabbitMQ, even your client doesn't have to be partitioned. It could be partitioned from one RabbitMQ node to another. The one that's remaining is going to say, hey, I don't see you talking anymore. I'm going to go and reclaim these items in case you crashed and hand them to other people. So now I hand out my lock to both sides. That's a real problem. We could prove it. So I ran Jepsen on this thing, and it spat out stuff like not linearizable. The linearizable prefix, the part of the history which was OK. There's a bunch of operations, and then we started this network partition. The Nemesis partitions the network into nodes N1 and N4 on one side, N3, N5, and 2 on some other side, and then some operations happen. We see that process 3 invokes an acquire operation on the mutex. Process 2 invokes acquire. Process 2 acquires complete successfully, right? So now process 2 holds it. Some other process tries an acquire, and then there's an inconsistency. We ran out of options when process 1 successfully acquired the lock. And Nasos can tell us exactly what happened in every interpretation of the system, right? Because there's many ways you could get to that point. So you'll see histories like 1 acquires the lock, 1 releases the lock, 2 acquires the lock, and then we've got a state, right? The mutex is now held, and there's some pending operations, and we can't go from a locked mutex and still acquire it. So we've shown that RabbitMQ locks allow double locking, right? You don't want to do this. This is a good thing for a queue. You want to re-queue elements when processes crash. You want idempotent at least once delivery, because that's how you build a reliable queuing system. But it's not linearizable. It's not really a lock service. And so if you want a lock service, you probably want to use something like etcd. Yeah, you know what's up. etcd is a little bit like Zookeeper. It's based on the Raft consensus algorithm, written in Go. It's got an HTTP API. It's very fast to start up, very easy to compile. Its API is quite easy to write a client for. You can do it in a couple hours. I quite like it. It's nice to see this sort of renaissance of simple, distributed, consistent systems. Although this one is fairly new, and so you might want to hold off if you're more of an enterprise crowd. It's designed to do configuration and coordination services, so you can use it for small pieces of state, pointers to other state, but you don't want it to be like a primary data store. But it's supposed to be linearizable. It gives us reads and writes and value index-based CAS. There's 2 types of reads, actually. There's a stale read, which happens on any node, And then there's a consistent read. If you set consistent true, it's going to go get the most recent state. And that's what we need for a linearizable system. First thing I found, race conditions. When you're joining nodes to each other in a RabbitMQ cluster, you'll get into these sort of awkward situations where if you join them any faster than like 1 per 5 seconds, the leader will start spinning on timeouts from other nodes that it thinks crashed and then refuse to accept new nodes. It made it really hard to get tested. But the etcd team is extremely responsive. They're very helpful, and they got the bug fixed in a matter of like 16 hours. So we went on to test it. This is what I found the first time. Not linearizable. We invoke a compare and set from 1 to 4. Somebody else reads 1, and that works. The compare and set from 1 to 4 succeeds. So now the new value is 4, followed by a read of the value 1. Okay, so let's think about the state, right? You see something like 4 writes 1, process 0 reads 1, process 3 reads 1, process 1 reads 1, process 4 reads 1, process 2 changes from 1 to 4, and now the value is 4, and there's 13,000 other worlds in which the value is always 4, but we read 1. You can't do that, right? It's not legal. If it were linearizable, it would be like saying, okay, the cas from 1 to 4 succeeds, and we've got this barrier, right? We're not supposed to see 4 anymore. We did this read, and it came back with an old value. It's stale. Right? This is extremely unsafe. But Raft guarantees us that the log entries in the system are supposed to be linearized. That's the whole point of the consensus system, right? So what's going on here? The answer is that the etcd consistent reads don't actually go through the Raft log at all. They read the state of the current primary node and then return immediately. So if you're familiar with a consensus system, like typically you'll have multiple primary nodes concurrently because you can't stop them from being concurrent. But they won't be able to both propagate state changes. So if one of them tried to do an operation, it would fail. That's what you want, right? But if you talk to a leader which still thinks it's a leader, even though it's dead, it could return its old state. So like, let's say there's a new leader on top and an old leader on bottom. The new leader does its cas from 1 to 4, compare and set, change 1 to 4, new state is 4, new state is 4, but it can't tell the old leader yet. And the old leader still thinks it's a leader because it's partitioned. And then you do your read against the old leader, and you see the old value because it doesn't know any better. So this is a problem, right? This violates linearizability, also violates sequential consistency and causal consistency and reads your writes and monotonic reads. It is terrible. Don't do this. And while I'm finding this, HashiCorp shows up. I wake up one morning and there's like 8 Twitter mentions, and they're all like, hey, have you tested this Nasos thing yet? And I'm like, I didn't even know it existed. There's a system called Consul, which looks a lot like etcd. It's another configuration and coordination service designed for process discovery. And they tested it with Jepsen before releasing. I'm like, yes, this is great. More testing. Exactly what we all want. And they say, actually, in our testing, Consul recovered gracefully from partitions without introducing any consistency issues. Well, that's terrific, Like, well done, guys. Except it's not quite the whole truth. They actually found the same bug that etcd did. They just didn't talk about it. You know how they fixed it? They changed the leader release timeout from 1 second to 300 milliseconds. So I'm going to ask you, have any of you written a race condition before? Raise a hand. Yeah, me too. A lot of them. How many times did changing the timeout make your race condition go away for a little while? Yeah. So this is a good thing, right? This is performance optimization. You're going to see the bug less often, but it's still there. It's lurking, waiting to come out. So I want to suggest that when you're writing a system that's not real time, right, one in which you can't guarantee the scheduler is going to wake you up on time, you can't get correctness by adding a timeout. You have to actually change the logical structure of the program. And we're going to see that later with Elasticsearch. So both etcd and Consul, we've all talked about this. They're going to try and make the reads actually consistent. There's going to be 3 flavors. One is a sort of lazy read where you can talk to any node, really fast, really available, but stale. A leader read where you usually get the most current state, but not always. And that's really helpful because if you're going to do compare and set, you want to reduce that window of contention. So talking to the leader dramatically reduces your retry costs. And then you'll have an actually consistent read where you have to wait a full round trip of latency for the node to confirm that it's still the leader before proceeding. And this is okay, right? A lot of applications can tolerate stale reads. If you're only doing reads and no writes, you can recover sequential consistency from this. So it's a nice spectrum, right? You get trade-offs everywhere. Moving on to Elasticsearch. Save the best for last. Elasticsearch is a search engine, a wonderful, well-loved one. It has sort of two internal parts. There's a database, and then there's a search index. And this is useful because search indexes are expensive, right? You don't want to update them all the time. So you do your consistent operation against the database, and then you replicate the database gradually to the index. You traverse it every so often, and then you write all the changes into new indices. Because index construction is expensive, and maintain those inverted structures takes a lot of writes. So your search is eventually consistent. The actual document fetching and updating should be consistent. And it offers in the API compare and set. You can write if and only if your version is equal to the current version on disk. That's what you need to build a safe sort of databasey system. And in fact, the write consistency notes say that by default, index operations only succeed if a quorum, that is half of the cluster and more, are available and acknowledge your write. This is what you'd expect from a CP system. But you go and look up, like, okay, what does the system do in a partition? And you find this thing from 2010, which says that when it comes to cap at a very high level, Elasticsearch gives up on partition tolerance. Well, I've asserted that you can't say that. So let's find out why. I personally believe that within the same data center, network partitions very rarely happen. And when they do, it's a small set, usually a single machine that gets partitioned out of the network. And in those cases, we could be safe. Okay, so if we work with these assumptions about the types of failures we're going to encounter, this algorithm could be consistent still. Then I see this from 2014. This is January. Elasticsearch gives up on partition tolerance. Again, it means that if enough nodes fail, the cluster state turns red, and Elasticsearch does not proceed to operate on the index. Oh, okay, so it goes unavailable during partition. Perfect, this is good, right? This is good. Elasticsearch is not giving up on availability. Wait. Okay. Every request will be responded, either true with the result or false error. I think we're operating under different notions of what availability means. So maybe it preserves availability and gives up on consistency. Consistency is not given up by Elasticsearch. Oh. So we don't give up anything. First, on the document level, you've got write and read consistency, da-da-da-da-da. After a node crash, Elasticsearch tries index recovery. It should always end in a consistent index state. Okay. They probably just don't know, right? Like, it's probably just an actually CP consistent system, and during a partition, it goes unavailable. It's not what you find. If you test it, if you do a bunch of compare and sets on a document, you'll see these little windows of write loss. So what's odd is that it looks safe from the start. Like, things seem to crash correctly. I cut off the network, and then I see all of my invocations time out. And that's what you'd expect from a linearizable system, right? It's like, I can't function when I'm cut in half until I elect a new primary, so I'm going to reject your requests or time out. It seems safe, and I do a final read, and I get all these numbers back, and I think it's good. But when I analyzed it, I found out that a couple of them were missing. Like writes number 176, 177, and 178, and 250 and 251, why those ones? I mean, the drop happened at number 49 and 50, so like why, like 67 seconds later did this thing disappear? It doesn't make any sense. So it throws away like 1 in 55 writes. I'm like, all right, maybe it's hard, right? Maybe this is just a consequence of the way they're thinking about partitions. The Elasticsearch model sort of assumes, I think, that partitions are symmetric, that they're reflexive and that they're transitive, right? That they're identity classes. So like once you partition network, they're going to be nice, well-contained chunks. But real networks don't always partition that way. I'm causing partitions like this. There's a node that bridges both halves. And in this configuration, every node thinks it has a majority, right? But neither of those two primaries can see all the other nodes, so they're not correctly updating each other. And that node in the middle is a member of both clusters. And you'll find exactly this kind of partition is possible. So with two primaries, you can lose compare and set updates. Let's back off. Let's say I'm just going to do NQs of new items. I'm just going to create new documents in the database, because those are always safe to merge, right? You just assign a unique identifier to every one of them, and then you use set union when you recover the partition, and every document you inserted is present. You can't compare and set, that's harder, but you can create. So Billy Mays here, with an exciting new database feature. Insert a document in the next 5 minutes, and you'll lose half your data. I started seeing these odd exceptions during the test. During creation of a new document, fresh document, never seen before, document already exists exception. Jepsen index 1. It's like 1, is that the document ID? Like maybe it's generating like sequential identifiers on both sides. So on one side it generates documents 0, 1, 2, 3, and on the other side 0, 1, 2, 3, 4. And when they merge, it has no choice but to throw away the documents with conflicting IDs. But if you go back and you look at the docs, it's like, no, IDs are 22 character long UU IDs, so those shouldn't conflict. But nonetheless, in the results, out of the set, it threw away 645 out of 1,961 documents. Like almost a third. And this is when the network was only partitioned for like half the test. So it threw away basically half of the data that was written during the partition. Just gone, right? Like how? I can't. So I thought, okay, maybe it's this conflict in IDs, and I went and like actually dug into the protocol, and no, it's actually, they are unique identifiers. So it's taking unique IDs on both sides, and when it recovers, it's just saying, screw it, I'm gonna throw away all the data? That doesn't make sense. And then you look at the code and you find things like this. If result.has conflicts, to do. What should we do? Okay, I'm not sure which actual write path this was in. I skimmed through all of the has conflicts functions and found lots of things sort of akin to this. It's not clear to me that the conflict resolution strategy was thought out, because if the partitions had occurred in the way that the model said, if we didn't see these kinds of weird partitions, if network partitions were rare and they partitioned single machines, these wouldn't even come into play. So if these weren't going to happen, why bother writing code, complicated code, to try and figure it out? Right, so this is a system that sort of shows, I mean, every system as it evolves, right, it shows traces of its past. Like if you look at a freeway, you know, it might have a weird kink in it, and that kink comes from the fact that it was rerouted to avoid a building that is no longer there. Or maybe when you rebuilt the freeway somewhere else, you had to build it sideways next to it, and so you had to move overpasses and things get funny shaped. Every system carries this kind of legacy, right? So while Elasticsearch is rapidly evolving and rapidly becoming safer, it still carries these sort of old assumptions with it, I think. This is not a theoretical problem. I want to read you a couple of the tickets opened in the various GitHub issues for these sorts of things. 11 months ago, suffered from this the other day when an accidental provisioning error had a 4 GB heap instance running on 4 GB of OS memory. The nodes swapped, the process hung, and the intersection issue described here happened. Network partition caused by running out of memory. We've been frequently experiencing this mixed brain issue in several of the clusters, up to 3 or 4 times a week. Network partitions are rare. We've always had dedicated master eligible nodes, correctly configured minimum master nodes, and have recently moved to 0903 and see no improvement. Our situation appears to be I/O weight related, in that a master node hits an issue that causes extensive I/O. The other nodes then fail and give up on the primary. So I/O can also cause network partitions. You wouldn't think of this, right? Like it's a single node system, but if that node pauses because you're doing system calls, and system calls can block, and sometimes system calls happen when you don't expect it. You ever S-trace a Ruby process? All sorts of file system activity going on. So this is unexpected, right? For my clusters, split brains always occur when a node becomes isolated and then elects themselves as master. I am experiencing at random times a spike in heap usage followed by long garbage collection. And after the nodes finish the long GC, the cluster is getting into a split brain situation where one of the cluster nodes is a member of both sides of the split. Minimum master nodes does not help because the node exists in 2 clusters at once. Moral of the story, Zendisco is terrible. Use Zookeeper instead. There are pluggable systems in Elasticsearch for sort of membership and discovery and leader election. Zookeeper's leader election, I don't think it's safe, but it's probably a lot more safe. So if you're using Elasticsearch, I strongly recommend you try that instead. And then also, I don't think you should treat Elasticsearch as a primary data store. There's a number of very well-written sort of knowledgeable blog posts that suggest that you can use Elasticsearch as your main database. I think this is crazy and that you should keep your data somewhere safe. So do your writes and reads to your main database, and then use Elasticsearch as a derivative store. You replicate asynchronously into Elasticsearch, which then replicates asynchronously from its own internal database into the search indexes, and everything is good, right? You weren't expecting immediate search anyway, so this doesn't really lose anything. And you get the nice property that if Elasticsearch corrupts its indexes, you can recover safely, right? Always design like this. You've got lots of systems. They're going to be tiered. You're going to have derivative stuff. You do this for performance reasons. Common architecture pattern. Doesn't mean Elasticsearch is bad, right? It's just optimizing for somewhat different things. So, to wrap up, we talked about theoretical models of consistency, right? And in particular, this strong notion of linearizability, that every operation happens between the invocation and completion, and it happens at an atomic single point in time. And then we use that constraint to examine different systems. But when I talk about these errors, I'm speaking of one very particular system, right? I'm talking about one failure mode. So if you're not basing your production database on a run of Jepsen on my computer using my network partitions, chances are these tests won't be reproducible for you. You've got to consider specific clients, specific versions, specific patterns of writes, specific timings, specific network topologies. All of these things are going to come into play, right? So I've demonstrated that a failure might be possible. It might not be probable. There are plenty of companies who get by just fine using inconsistent databases, like using replicated Redis as a primary data store. You can do that, right? And you can build a successful business and you can get a successful exit and never have data loss, or you could have data loss and not notice, right? This is not the end of the world. A lot of companies find it actually cheaper to pay human beings to clean up their broken data, right? You have minimum wage people, or you have like $60,000 a year support engineers coming in and apologizing to human beings for messing up and rewriting the structures, so that they actually make sense. Banks do this all the time. So, is your system safe? I don't know, right? I've told you these things are possible, but it's going to be up to you to find out if your own systems are correct. You should think about runtime pauses, right? It's not just a network property. I'm causing network partitions, but they can also be equivalent or isomorphic to runtime issues like garbage collection, like thread starvation, like I/O. The network can be slow. It often doesn't partition cleanly. A lot of times you just get packet loss. So like one direction's really slow and the other direction's fast. Or one direction's gone and the other direction's fast. You'll get one-way partitions all the time in production. If you rely on clocks, right, for scheduling, it's really tricky to do this, right? Wall clocks are not monotonic. POSIX time will jump backwards by definition. So if you think that POSIX time always rises and that you could subtract time 1 from time 2 and always get a positive number, you're wrong. That should probably scare you. The important thing is that clocks are a really good way to get human scale systems, right? Like having an actual timestamp on something helps you figure out roughly when it occurred, but it's not enough for consistency. Clients are an important part of your distributed system. I think Jeff Hodges talked about this yesterday. We're used to thinking of the database as being this sort of monolithic source of truth and the clients as being dumb, but the clients are actually maintaining state machines, right? Maintaining TCP connections. They have specific semantics around the ordering of operations in the client and the order of operations on the network. TCP sockets, for example, don't give you ordering constraints if you have 2 at once, right? Things can pass faster on one stream than the other and arrive out of order. All sorts of really subtle consequences there, and you have to think about the clients themselves. Ultimately, because this kind of thinking is hard, you should try to limit it. Only think when absolutely necessary. You should think about the stuff that has the most critical impact. Things like user creation. You don't want to have duplicate user IDs. That's going to be really bad. So those should probably go in a linearizable data store. You don't want to charge people money twice. If you're moving money around, you really don't want to lose linearizability, right? Look at the, 3 or 4 now, folded MongoDB-backed exchanges or whatever that didn't understand transaction scope properly. So you do a read and then a write outside of transactions, and it can freely reorder them or distance them with other operations, and so you could lose money, right? Thinking about linearizability matters in some cases, but often not in all of them. How much safety is really necessary, right? It can be okay for you to lose a lot of data, especially if you're running a social network. On Facebook, only 10% of your posts actually show up on other people's feeds anyway, right? So if you mess up somebody else's derivative feed and lose some items, it's okay. If you misorder items, it's okay. Twitter, for example, the direct message notification light is inconsistent on the scale of weeks to years. So this might not be critical, and it's up to you to figure out where those performance and complexity trade-offs lie. You have to balance performance, right? The weaker consistency models are faster in general. Weaker consistency models are weirder. Weaker consistency models are more available. So you'll have a continuum. You'll likely have several production systems with different types of consistency strengths. And you need to measure them. It's not enough to have a system, a database that is known to be correct, right? It's possible to use Zookeeper extremely wrongly and get weird non-linearizable results. So you have to think really carefully about what's going on and measure it, right? Actually test it. So if you use IP tables, you can cut off network partitions in prod. You can use TC to cause like packet loss and model delays. You can actually go and cause a bunch of disk havoc. You can suspend VMs. Right? Write a client that hits your API, does a whole bunch of operations and logs them, and then pass it to some sanity checker. Right? Verify that the operations you think succeeded actually made it through. You have to test your whole system end to end because every one of those pieces is causally linked to the next, right? It's not enough to just test your API alone. You have to test the API plus the database plus the derivative services. So combinations of layered testing, functional sort of per function or per method tests that encompass your entire module, tests that encompass the whole system, tests that encompass the composition of that system with its neighbors, and then integrated tests that test the whole thing, whole chain. What I want to emphasize is that a lot of these systems have not had proper testing. Cassandra, for example, in 2.0 announced the release of a lightweight transaction system, which is linearizable, except it's not. It had lock issues where if you did concurrent operations on the Paxos implementation, it would deadlock hard indefinitely. You could never write to that object again until you manually cleared the system.paxos table. How does this get into production, right? Did you not try this? And then, of course, once that bug was fixed, it turned out that it lost transactions anyway, so that was another problem. MongoDB lost data at every consistency level, including the strongest one, majority. That bug is now fixed, but there's another, I think. So you would be shocked what these systems will do. A lot of the databases that we know and love and trust haven't had attention put into them, or were designed initially with expectations about their environment which might not hold anymore. The expectation that network partitions are rare, the expectation that disks don't fail, the expectation that messages are not reordered, that time is reliable, those get encoded in subtle places in dozens of ways through your system, and it's hard to rethink from the ground up sometimes. So you should test your systems. I owe a deep debt of gratitude to Peter Bayless, Bob Pokert, Kelly Summers, Aman Dagar, Joseph Blumstead, Aaron France, Alvaro Videla, Jacques Fuentes, Jiang Li, and Tyler Schuett for their assistance in putting this presentation together, for research, and for helping with consistency models. Comcast for funding the actual machines that made this possible, Factual for keeping food on my table, and many others. Thank you all very much for coming. We have our own consistency issue in that there are many people pipelined for lunch, so I'm happy to entertain as many questions as possible. Over there. Where does DynamoDB fall in the spectrum? The Dynamo paper is definitely in the highly available weak side of things. It looks a lot more like React or Cassandra. DynamoDB, I think, has a much stronger model. I think it offers linearizable transactions, but I'm not sure, so don't quote me on it. Yes?
Same question, but substitute
Neo for J, no idea.
So you read before how, this is kind of like engineering work to test the assumptions that these databases can provide. What do you think is what's the next Jepsen-like test that you would like to see?
What is the next Jepsen-like test that I would like to see? Honestly, there's a lot of ground to cover with this tool. So this can now test a stronger class of consistency, which means that there are new types of databases. I can actually test Postgres, for example. And I want to try and look at the subtle differences between snapshot isolation and full serializability. I think that would be an interesting thing to test. I also want to test clock skew drift more robustly. I've simulated it with a couple systems, but I want to have it automated. And also I want to simulate I/O wait times. I need to figure out how to interrupt a process without actually having access to the source. So ideally, I can force it to pause on a system call, and then I can use that to introduce timing asynchronicities.
Can you talk briefly about clocks? Last time I paid close attention to clocks, what I read was, oh, NTP solves it because it never goes backwards, it always just goes forward more slowly. So that was old, that was a long time ago, so is that not true?
Yeah, so NTP says that clocks are monotonic, so is this still a problem? Monotonic clocks are better than non-monotonic clocks, certainly. POSIX time, by definition, is actually linked to UTC, and UTC time is exactly 864 seconds, or 864,000 seconds per day. So when there's a leap second, it repeats, right? It jumps backwards or forwards by a second, which means it's not monotonic. So a correctly behaving POSIX clock will jump backwards. What some systems do, like at Google, is they, using their NTP servers, they slew the second out over the whole day. So every second is slightly longer than it should be, and then they don't have the irregularity. On top of that, NTP has interesting failure modes. A lot of times it is not running or not configured. I run a monitoring project called Riemann, and one of the things that we have in the topic is clock skew party detection line. Because so many people say it's not working or what's weird, and it's like, oh, your clocks are not synced. But I run NTP. No, I'm not running NTP in that box. It happens to me too. You know, it's just hard to get these things to sync. Yeah. What's up?
I don't have a question. Just on behalf of Aaron France and my employer, thank you for your help with Elasticsearch and for Jepsen. And I've got you a T-shirt from Aaron. Thank you very much.
You. Yeah, I want to reiterate that everybody building these systems has been really helpful in finding these bugs. And much as I wail on their consistency properties, there's a lot of really good stuff and really good engineering happening here, right? So I'm not trying to say they're bad. I'm just finding these specific corner cases, and if you care about them, then you should be concerned. Anything else? All right, well, I'll be hanging out after this. Thank you all very much.